On the table is a single power die pulled from a silicon carbide module built for either an electric vehicle inverter or a grid converter, its casing still carrying the faint discoloration of a reflow oven. This is not a logic chip chasing the smallest transistor on the planet. It is a switch built to survive hundreds of volts and real heat, and that distinction changes every rule usually applied to a chip on this table. We will take it apart layer by layer, from the crystal it was grown on down to the solder that carries its heat away, and the deepest layer will not say what the surface suggests, because the buried fact here is not about a missing machine, it is about a missing fight. The passes run through the substrate, the epitaxial layer, the gate structure, the package and heat path, and finally the line where mature node manufacturing quietly out argues the entire smallest transistor race. The first incision exposes the substrate, the crystal body the entire device was grown on. This die sits on a silicon carbide boule grown by a slow, defect-sensitive process called physical vapor transport. Chinese substrate makers including Tanka Blue and SICC have published roadmaps and supply agreements claiming meaningful volumes of 4-inch and 6-inch silicon carbide boules. That claim is repeated across multiple domestic suppliers, but independent third-party defect density benchmarking against Wolfspeed's mainstream substrate is not publicly available. So what sits in front of us at this layer is the company's own claim, not a verified parity result. This layer exists because everything built above it inherits its flaws. A boule carrying too many micropipes or basal plane dislocations cannot be rescued later by a clever gate design, so the first cut has to be the crystal, not the circuit. The fact that this die was grown at all on a domestic boule is the precondition every later claim depends on, and that precondition is harder to satisfy than it sounds, because on a power die, a single dislocation under the active area is not a quality statistic. It is a field failure waiting inside a vehicle moving at highway speed, which makes the defect threshold on this wafer a safety boundary rather than a grading curve. The next pass down exposes the epitaxial layer, a thin film of silicon carbide deposited on top of the substrate by chemical vapor deposition. This is where the device's actual blocking voltage and current path are formed, and historically this has been the harder domestic milestone because uniformity across a 6-inch wafer is a tighter requirement than simply growing the wafer underneath it. Chinese epitaxy producers, including SICC, along with several joint ventures formed with automakers, state qualification for automotive-grade epitaxial runs. Several electric vehicle makers, including BYD's and House Power Semiconductor Unit, have reportedly moved parts built on these claims into production vehicles. What does not yet exist is the long-term field reliability data that Infineon and Wolfspeed have accumulated over a decade of automotive deployment. So the domestic claim is real in the sense that it is shipping, and unproven in the sense that nobody has logged a decade of failures or non-failures against it yet. The substrate proved the country could grow a crystal. This layer proves it can grow a working device on that crystal at the thinness and uniformity a power transistor actually requires. And that gap between owning a raw material and owning a functioning semiconductor is exactly what this incision closes. Beneath the epitaxial film sits the gate structure, the part of the device that physically turns the switch on and off. Silicon carbide carries a known industry-wide reliability challenge at this layer because its gate oxide traps charge at the oxide semiconductor interface more readily than plain silicon does, a physics problem every silicon carbide maker faces regardless of where the fab sites. Domestic Chinese fabs report using planar and trench gate architectures broadly similar in concept to the designs Infineon and Wolfspeed have already published, and several Chinese suppliers state internal qualification testing across automotive temperature ranges. None of them have published the kind of long-duration, high-temperature gate stress data the established Western suppliers have made public across multiple product generations, so the claim sits ahead of the proof at this layer specifically. What matters more than the reliability gap is the scale of the structure itself. Silicon carbide power devices are built on feature sizes measured in micrometers, not nanometers, and a gate this coarse simply does not require the extreme ultraviolet lithography tools the export restrictions were built around. This is the first layer where the buried fact stops staying buried and starts to surface on its own. The fourth incision exposes the package and the heat path, the stack that proves the device can survive the job it was built for rather than merely demonstrate that it works on a bench. The die is bonded onto a substrate carrier and then onto a base plate with the entire stack engineered to pull heat out from underneath rather than off the top, because inside an automotive inverter, the device absorbs both its own switching losses and the engine bay's ambient heat at the same time. Chinese module assemblers, including units tied to BYD and CRRC, along with several power module joint ventures, state mass production of automotive silicon carbide modules using double-sided cooling and sintered silver die, attach methods comparable to what Infineon documents in its own automotive module literature. That claim is supported by the fact that these modules are already riding inside delivered vehicles, not just demonstration boards. What remains unpublished is any independent third-party thermal cycling lifetime test comparing a domestic module directly against Infineon's automotive packages or Wolfspeed's equivalents, so the comparison again rests on shipped product rather than a neutral teardown. A power die that cannot survive its own packaging is a laboratory result. The fact that this exact stack is already on the road is the layer that turns a substrate claim and an epitaxial claim into an industrial one. The deepest pass does not expose another physical layer of the die. It exposes what repeatable domestic production at this scale actually proves about where the strategic contest sits. Every layer dissected so far was built on processes and lithography generations that, by logic chip standards, are old, and silicon carbide power fabrication runs on equipment that Chinese toolmakers and foreign vendors outside the tightest export restrictions can still supply. Multiple analyst estimates place China's share of global silicon carbide substrate capacity additions over the next several years as the largest of any single country. That is a projection, not a settled fact, but it tracks with the volume of fab expansions already announced by Tanka Blue, SICC, and others. This is the layer where the channel's recurring argument surfaces without needing to be stated outright, because the restriction architecture built around extreme ultraviolet lithography was engineered to choke a different kind of chip. A silicon carbide power switch was never going to need that tool, not now and not at any later point on its roadmap. The country that cannot yet print a competitive sub-10 nanometer logic die can still print a competitive power die at scale, because the contest in power electronics was decided by crystal purity, epitaxial uniformity, and packaging discipline, three fights the same restriction architecture left completely open. This object on the table is the proof of that, not a press release describing it. Picture the difference between these two kinds of chip as two kinds of plumbing inside the same house. The logic chip is the finest filtration membrane money can build, where a single misplaced pore ruins the entire filter. The power die is the load-bearing pipe carrying the actual current through the wall, where what matters is not how fine the pore is, but whether the pipe holds under pressure and heat for 10 straight years without cracking. The restriction regime took away the machine that makes the finest membrane. Nobody needed to take away the machine that makes a pipe that simply has to hold. Three things this dissection cannot settle deserve to be said plainly rather than smoothed over. The claim of automotive-grade qualification and mass production is supported by vehicles already on the road, but the multi-year field reliability record Infineon and Wolfspeed, built across a decade of deployed inverters, does not yet exist in public form for the domestic parts at comparable scale. No independent laboratory has published a direct comparison of defect density, gate oxide reliability, or thermal cycling lifetime between a current generation domestic silicon carbide die and the equivalent Infineon or Wolfspeed part, so every comparison in this teardown rests on company claims and analyst estimate rather than a neutral benchmark. And the physical limits are shared by everyone in this material regardless of nationality: the gate oxide trapping problem, the difficulty of holding defect-free yield as bowels scale past 6 inches, and the packaging stress of repeated thermal cycling, with nothing here showing whether the domestic supply chain has matched the established yield curve at the coming 8-inch transition, only that it is moving toward it in public. None of that changes the core finding on the table. The contest this die was built to win was never the smallest transistor race, and on the terrain that actually decides power electronics, mature node crystal growth, and packaging discipline, the gap that matters is narrowing in shipped product, not in a slide deck. Taken together, the 5 layers of this die do not describe a chip that slipped past export controls through some clever workaround. They describe a chip that was never standing in those controls' way to begin with, built by a supply chain that understood that distinction before most outside observers did, and chose to win the fight the rules left open rather than the fight the rules were written to close. The smallest transistor race was never the only race running, and this die sitting here is what winning the other one actually looks like. If the reach of that restriction has a visible edge in silicon carbide, where else across the power and analog side of this industry might that same edge be sitting unexamined, and which object would you put on this table next? Subscribe and turn on notifications because the next teardown is already on the bench waiting to be cut open.